Alright, so good evening again. We can start from where we left last time. So last time we started to talk about systems that have more than 1 degree of freedom. So of course the very first transition that we should do is from 1 degree of freedom to 2 degrees of freedom. We said that there are a few things that we should look at when we make this transition between single and multiple degrees of freedom. So first of all, when we talk about 2 degrees of freedom, we are not going to look at one natural frequency anymore, but we will start to look at as many natural frequencies, as many degrees of freedom we have. So 2 degrees of freedom means 2 natural frequencies. We will also look at more equations of motion because we will have more degrees of freedom. So for every degree of freedom we will have a specific equation of motion. These two equations of motion are coupled to each other, which means that we end up with a system of equations, and in order to solve this system of equations we need to look at all the equations at the same time. And this is probably what makes multiple degrees of freedom systems more complex than single degree of freedom system, even if maybe next week or next time we will see a way to actually decouple the equations of motion. Also, another consequence is that since we work with systems of equations, we are going to use a matrix form for basically all the systems of equations. So we started from the most simple case that we can analyze, which means we have two masses that are connected to each other through a spring K2, and then the first mass is connected to the wall through spring K1. We also specified that we need to pay attention in order to determine the number of degrees of freedom, because in this case it seems obvious that with two masses that can move independently from each other we have 2 degrees of freedom. However, we can have 2 degrees of freedom even if we have only one mass. For example, in this case, if the mass can move horizontally and vertically, it means that we still have 2 degrees of freedom. Or we looked at the example of the car with the suspension. So in this case the car can move in the vertical direction because the two springs can be contracted or stretched by the same amount. But if the two springs are contracted or stretched by a different amount, it means that we have also a rotational degree of freedom. So again, the number of masses is a good indicator, but it's not enough to determine how many degrees of freedom we have. So once we started from this one, we can proceed exactly in the same way we proceeded so far when we're looking at single degree of freedom system, because we need the free body diagram of the two masses in this case, and then once we have the free body diagram we can do summation of forces equal to mass time acceleration. Of course, when we apply summation of forces equal to mass time acceleration, we need to specify which mass and which acceleration. So here we have, for the first mass, summation of forces equal to m1 x1 double dot. For the second mass we have summation of forces equal to m2 x2 double dot. In this case, of course, all the forces are in the horizontal direction, so we can consider all the forces for the first mass, all the forces for the second mass, and then we can rearrange and we obtain these two equations. This is for the first mass, this is for the second mass. We can rearrange in order to order according to the degree of freedom. So this acceleration of first mass, displacement of first mass, displacement of second mass. Here we have acceleration of the second mass, displacement of the first mass, and then displacement of the second mass. So we start with the accelerations first, and then we go to the displacements. In this case, same thing, we start with the acceleration and then we go to the displacements. We can write this in a matrix form, so we have m1 and m2 that multiplies the acceleration vector, and then we have the stiffness matrix that multiplies the displacement vector, equal to 0, 0, because it's not a forced system. We also said that basically we can compare this equation in the matrix form to the equation that we are using for single degree of freedom systems, because in that case we had mx double dot plus kx equal to 0. Same thing here, we now have, instead of just one mass, we have a mass matrix. Instead of the acceleration of the mass, we have the acceleration vector. Instead of the stiffness of the spring, we have the we have the stiffness matrix, and then instead of the displacement of the mass, we have the displacement vector, which are listed all here. The solution of this one can be written in this form, and we can do the exact same thing that we did before, which means we have to derive twice in this case. Once we derive twice, we can plug the second derivative and the function in our general equation, and this is what we obtain. How do we solve this equation? The term u cannot be 0 at this time because it means we have 0 amplitude, so physically not valid solution. This is an exponential, it cannot be 0, so we must look at the term between parentheses, which is, remember, a matrix, because both m and k are matrices. So when we look at the term between the parentheses, within the parentheses, we have this matrix, so we have to calculate the determinant of this matrix, we equate to 0. These are the steps to calculate the determinant, which means we end up with an equation that has as unknown omega, which is the natural frequency of the system. Of course, in this case, we end up with more than one natural frequency, which is what we said before. Theoretically, we end up with 4 natural frequencies because this is the 4th order. However, we know that when we solve this one, we will have 2 couples of solutions. One will be plus or minus a certain number, the other one will be plus or minus another number. So basically we can look only at the positive values, because those are the values that have physical meaning in terms of frequency. Negative frequency doesn't really mean anything. So we looked at an example where we plugged certain numbers for masses and for stiffnesses, and then we found that the frequencies are plus or minus square root of 2, plus or minus 2. Of course, as we said, we look at the positive values, which means we look at plus square root of 2 and plus 2. Now that we have these 2 values of the frequency, which means we are done with basically the first unknown that we have, the first unknown that we have in our solution, omega, then we have to work in order to find this unknown for our solution. So we start by looking at the first natural frequency. We said that natural frequencies are sorted in increasing order, so which means in this case omega 1 would be square root of 2, and then omega 2 would be 2, simply because 2 is greater than square root of 2. So when we plug the first one, we have negative omega 1 square m plus k times u1. In this case, our unknown becomes u1, which is a vector with 2 components, u11 and u21. We can do all the summations and the products, and then we end up with this system of equations. So these 2 equations are actually the same equation. If you simplify, you can obtain the exact same equation, which means that in order to solve this one, we need to set one of the 2 values arbitrarily, and then we can find the other value, the other component of this vector. So by doing this one, we can set u to 1 equal to 1, and then we will have as a consequence that u11 will be equal to 1 over 3. So by doing this one, we obtained the first vector. Later actually we will give names to these vectors. So the first vector, big U1, would be 1 over 3, 1. And this is where we stopped last time. Any question about all these steps? Okay, now we need to keep working because we are not able to plot the solution yet. So we found the first u vector, so big U1. So now we have to do the same thing with the second natural frequency with omega 2. So we have to do the same that we did here. We did here with the second natural frequency. So we plug our omega 2 this time, so we'll have negative omega 2 squared times m plus k. This multiplies, in this case, our big U2 equal to 0. Now we are going to do the exact same steps, so I'm not going to rewrite all of them. I will write the final system of the two equations, which means that what we obtain is the following: is negative, so few steps again, just algebraic steps. So we have negative 9u12 minus 3u22, and then the other equation would be negative 3u12 minus 1u22. This will be equal to 0, and this will also be equal to 0. So as you can imagine, in this case we obtain the same thing, which means that we have two equations that are actually the same equation, because if we simplify this on top by 3, we obtain the exact same thing, which means that we can also set one of the two quantities arbitrarily. So we can set, for example, in this case, I have u22 to be equal to 1, and then as a consequence we obtain that u12 will be equal to negative 1 or 3, which means that our vector big U2 would be equal to negative 1 over 3 and 1. So now we are getting closer to what our final solution will be, because now we can write the final solution in actually different forms. We can write with exponentials, or we can write with frequency and phase. So we will use this last way to write the final solution, so with frequency and phase, and then including all the quantities that we just found, the frequencies and these these are eigenvectors, so these u1 and u2, we can write the solution as follows. So we have x of t equal to a certain constant a1 that multiplies omega 1t plus phi1 times big U1 plus a2, so here we have the summation of two contributions, and then this multiplies omega 2t plus phi2 and then times u2. So this is the best way actually to represent the solution, because this is actually the physical form of the solution of the system, because if we write the equation in this way, we can see that both masses oscillate at both frequencies, and they are both influenced by the two vectors u1 and u2. Now we can expand, because of course remember that we have to find two solutions. One will be x1 of t, the other one will be x2 of t. So we can expand this so that we can include both both solutions, and then we will find how to find we will figure out how to find the final one. So this big X is of course a vector of the two solutions, so we will have x1 of t, and then the second one will be x2 of t. So So this will be equal to A1 this is sine of omega 1t plus phi1, and this multiplies the vector u1 that we found before. So the two components were u11 and u21, and then we have to add the second contribution, so we have a2 sine of omega 2t plus phi2, and this multiplies the second vector that we found before. So we have u12 and then u22. So basically, when we look at the equation, the solution of the equation in this way, we will have the displacement of the first mass, which is x1 of t, equal to a1 sine of omega 1t plus phi1 times u11 plus this term that multiplies 1u2. For the second one, we have that x2t equal to, again, a1 sine of this quantity that multiplies this one, the second term of this vector, plus this term that multiplies this vector as well. Excuse me, this component of the vector. So, can we plot the solution now? If you remember, when we are looking at single degree of freedom systems, at this point we were not ready to plot the solution because we needed to introduce something else. Any suggestion? So if you remember, we were talking at some point about initial conditions, and at this point we have to do the same thing, because if you see the solution, again the two solutions, because we have two equations, we have these two terms, a1, actually these four terms, a1, phi1, a2 and phi2, that are still unknown. So we cannot plot the solution. We can have a qualitative idea of how the solution would look like, but we cannot physically plot the solution. This is because we need to find a1, phi1, a2, phi2. So it means that we have to introduce now the initial conditions. So how many initial conditions do we need? We need two initial conditions for each mass, actually, because here we have four unknowns, so it means we need to find like four conditions. We need four equations. How do we obtain these four equations? For the four initial conditions, and two will be from one mass, which means initial position and initial velocity of the first mass, and then we will have initial position and initial velocity of the second mass. So now, to simplify a little bit our notation, we can actually plug the numbers that we had before, because omega 1 now is known with the numbers that we used before. These two components are also known. Omega 2 is known for what we found before, and these two components are known as well. So we plug all the numbers and we see the two solutions. This is how they look like. So we have x1 of t, so the displacement of the first mass, will be equal to a1 sine of, in this case we put square root of 2, because remember that was our omega 1, square root of 2 times t plus phi1. Again, at this point phi1 is still unknown, that multiplies the first component of the vector u1, so will be 1 over 3. And then plus a2 sine of 2t. Remember, the second natural frequency was 2, so we can plug 2 here, plus phi2. Phi2 is still unknown, and then we multiply by the first component of the second vector, which was negative 1 over 3, I think, yes. We can look at the solution at the displacement of the second mass, so we have x2 of t. Similarly, we will have a1 sine of still square root of 2 times t plus phi1, and this multiplies 1 because it's the second component of the first vector, plus a2 sine still 2t plus phi2, and then we look at the second component of the second vector, which is 1. So we said that we need the initial conditions, and we said that we need 4 initial conditions. So the 4 initial conditions again are initial position and initial velocity of the first mass, and then initial position and initial velocity of the second mass. So we can use, for example, these values. And then we have x2 0 equal to 0, and then we have x dot 1. So we have x1 of 0 equal to 1, for example, so the initial displacement of the first mass is equal to 1, the initial displacement of the second mass equal to 0, initial velocity, because it's x dot, of the first mass, we can put this also equal to 0, and then the initial velocity of the second mass is also equal to 0. So what are we supposed to do with these 4 conditions? We can look at, yeah, go ahead. Exactly. So first of all, we can look at t equal to 0 for at least the 2 positions. These are already the position functions. So we can simply plug 0 here, here, and here, and equate to this first and then to this one, right? Because this is the first, this is the initial displacement of the first one, this is the initial displacement of the second one. And then what do we do with these two? Exactly. And then with these two, we can simply derive the first equation, we can derive, with the first function, we can derive the second function, we plug 0 at t for the 2 derivatives, and then we can equate to 0. So in this case, we have basically 4 algebraic equations, we have 4 unknowns, a1, a2, phi1, and phi2. We can simply solve these 4 equations, and then when we solve the 4 equations, we can finally find a1, a2, phi1, and phi2. I want to give you like just a couple of minutes to, again, just think about, so because it's just a matter of algebraic steps actually. So again, I want to give a couple of minutes just to organize the ideas on how to actually do these steps, and then we can look at them together. So I actually wrote down what we obtain when we calculated the derivatives and we plug t equal to 0 in our functions and in our derivatives. So this would be the first relation where we have x1 of 0 equal to 1. This is the second relation, which means we have x2 of 0 equal to 0. This is the third one where we have x1 dot of 0 equal to 0, and then this is the fourth one where we have x2 dot equal to 0. x2 dot of 0 actually. Forgot to plug in. So as you can see here we have again 4 equations, 4 unknowns. Of course we have also sines and cosines, so we need to work on some substitution for this and rearrange the equations accordingly and the unknowns accordingly. So even in this case we can do by hand, or we can use like a software to solve this system of equations, but eventually when we solve this one we end up finally with our solution for the 4 constants a1, a2, phi1 and phi2. So we'll have that a1 is equal to 3 over 2, then we have that a2 is equal to negative 3 over 2, and then we have that phi1 is equal to actually phi2, and these are both equal to pi over 2. So now that we have these 4 constants, we can plug the 4 constants here in the first and the second solution, and after simplifying a little bit, again you can go through the actual steps, but eventually if we again plug these 4 constants and simplify a little bit, this is what we obtain. x1 of t will be equal to 0.5 sine of square root of 2t plus pi over 2 plus 0.5 sine of 2t plus also pi over 2. And then for the second one we obtain 1.5, which is basically this number here, 3 over 2 sine of also square root of 2t plus pi over 2, and then minus 1.5, which is basically this negative 3 over 2 sine of 2t plus also pi over 2. Any questions so far? So basically now we finally have the final solution, because we have the function that describes the displacement of the first mass, which is this x1t, and then we have the function that describes the displacement of the second mass as well, this x2 of t. And actually we have all the numbers, because we have all the amplitudes, and then we have the frequencies, and we have the phases. And actually we can see from this notation here that we cannot isolate the two masses as a simple combination of two 1 degree of freedom systems, but there is some coupling. It means that both frequencies influence both masses, because as you can see here, this square root of 2 shows up both in the first displacement and in the second displacement. Same thing for these 2, which was like the second natural frequency, this shows up here and here as well. So now that we have all these numbers, we can actually plot the two functions, and this is how the plot actually would look like. So here we have the dark line is the displacement of mass x1, and then the orange line, this one, is the displacement of mass m2. Again, of course, this is based on the values of mass and elastic constant that we used before. So as you can see here, we cannot identify simply one frequency of oscillation for each mass, but they are combined. Anyway, there is something that we can do to try to figure out if we are in the in the right path to determine if these two curves, these two plots, are correct. What do you think we should look at? And we mentioned this one also when we were looking at the single degree of freedom systems. When we plot the response of of a certain vibrating mass, there is always at least one thing that we should check when we look at the displacement. Say again. Frequency ratio is something that we look when we compare the natural frequency with the frequency of the external force. So in this case we don't have any external force because we are still talking about free systems. We only have the two masses, we don't have external force. So another thing that we should look at are actually the initial conditions. Because if we look at the initial conditions here, remember we had that the displacement, the initial displacement of mass 1 should be equal to 1, and here when we look at the plot for mass number 1, the initial displacement is actually equal to 1. So it means this matches what we had in mathematical form, right? The second thing is that the displacement of the second mass at the beginning must be equal to 0, which is exactly what we have here. This is mass number 2. At 0 time we have no displacement, which means that this should start from 0. Exactly. The slopes are also 0. If we look at these two, we know that the initial velocity must be equal to 0, which means the velocity is the derivative, mathematically is the derivative of the displacement, which means that when we graph would be like the tangent, so the slope. So it means that the slope here must be horizontal, the slope here must also be horizontal. And if you look, you see that this is actually how it starts. Both of them start. So we have like a initial instant where we like horizontal, and then immediately the x2 goes up and then x2 goes down. So when you plot the functions and then these two conditions are met, very good chance that the entire graph is correct. At least you are on the first, on the right path. Makes sense? Any questions? Yes. Well, the homework. So the question is, with this multiple degree of freedom, the calculation will become more complex and more long. That's true. So this is actually the process that we need to follow. Generally, when you deal with multiple degree of freedom systems, 2 actually is probably the most simple that you can find. But actually, all these steps can be automated. You can actually write like a code to go through all these steps. because again you will work mostly with matrices, and you can simply automate all these steps using MATLAB, Python, basically whatever you want. Now for the homework, I will probably ask you to go through these steps for some of the problems by hand, so that you familiarize with the actual process that is needed. And then again, I think that would be needed at least a little bit to familiarize with the process. Make sense? I didn't think about the homework yet for this for this topic. Let's see, probably after Wednesday's class. Any other question about this? Alright, so we can look at an example which is still about 2 degree of freedom system, but it will be a little bit different at some point, and then we will see how it differs from what we have now. So we can look at an example where we still have 2 masses. So let's do this. So this is mass m1, this is mass m2, and we have numbers for this one. So we have the 2 masses are actually the same, so we have m1 equal to m2 equal to 2000 kilograms, and we also have the value of the elastic constant of the spring. So here I have that K is 280,000 Newton over meters, and then we have to find the equations of motion. Then we have to find the natural frequencies. Then we have to find U1 and U2, even if in this case we will look at more details on this, and then we can find the final response. To find the final response, of course, we need the initial conditions, so we can use the following initial conditions. So we have x1 of 0 equal to 0, and then we have x2 of 0, x2 of 0 equal to 0.1, and then we have x1 dot of 0 also equal to 0, and x2 dot of 0 equal to 0 as well. So I want you to spend a few minutes at least to start to think about the equations of motion and natural frequency, and then we will look at the other steps together, but at least you can start to think about what we should do in order to find all these quantities. So I'm going to open, I know we have just a few people, but probably can have a couple of breakout rooms, so you can discuss a little bit. let's do 2.